Okay, so today we'll concentrate on symmetric powers. So there are many ways of defining symmetric powers as well. One could define using universal property, but like tensor powers, we could have we defined using the universal property as well, right? So a tensor product of two things was came with a bilinear map and with some universal properties. Similarly, symmetric power, you can do that way, or we can define it as a quotient of tensor power, because we have already defined tensor power. We can define symmetric using that. Yeah? So let V be a vector space of dimension n. So most of the definitions doesn't require V to be even finite dimensional. Yeah. But I mean, we'll only think about finite dimensional vector spaces in this course. So we can start imposing dimension, but most of what I'll say today doesn't really require V to be even a finite dimensional vector space. So sim AV is where A is some positive number is TAV modulo, you quotient it out by submodule generated by subspace generated by these kind of vectors V1. So a typical element in so elements of TAV looks like sums of V1 tensor, V2 tensor, Vn, Va. So you quotient it out by subspaces of the form V1 tensor, V2 tensor, Va minus V sigma 1 tensor, V sigma 2 tensor, V sigma A, where Vi's are some elements of V and sigma is in the symmetric group on A letters. Yeah. So you want to, basically in sim AV, we don't want to distinguish between V1 tensor, V2, and V2 tensor V1. We want to identify those two. Yeah. So we quotient out by the subspace generated by these kind of ways. So that is that you can take it to be your definition of sim AV. Okay. So maybe by convention we will take, so this is if A is greater or equal to, you can take this definition, and maybe for convention we will take sim 0 V to be just the base field K, and sim 1 V should be the vector space V. So you don't do anything to so you don't quotient out by anything if A is less equals 1. Okay, so it comes with a multilinear map from A copies of V to this guy, this sim AV, and this multilinear map happens to be symmetric. So what is that multilinear map? You take A copies of V and you send it to V1 dot V2 dot VA dot VA. Yeah, and this by definition is the image of this guy. Yeah, so in sim AV, the notation we use for V1 tensor V2 up to V8 tensor V8 to be this dot. Yeah, instead of tensors we use dot. Tensors and bars we use dot. Okay. So phi is this this map, and of course phi is multilinear. Yeah, because it factors through TAV. So you take the map to TAV and then quotient out by something. So the initial map was multilinear. So then you're quotienting out by a subspace. So it remains multilinear. And it's symmetric because of the construction. Yeah. So note that phi of V1 to VA is same as phi of sigma V sigma 1 to V sigma A, because their difference lie in, so meaning the difference of their images lie in the subspace we are cosenting out by. Yeah. So phi is symmetric multilinear map. Okay. Is that okay? The definition is clear?
Yeah.
So so you can define it via the universal property, in the sense that this has the universal property. So this is a universal object for symmetric multilinear maps from A copies of V to another vector space. Yeah. To any vector space. So more precisely, if theta is a multilinear map from A copies of V to another vector space U, yeah, U is also a vector space. Then theta factors through theta uniquely. So it's a universal property. So theta uniquely factors through phi. Okay. So in other words, given this theta from A copies of V to U, they exist a unique map theta tilde from sim AV to U, which makes this diagram commutative. So that is theta is same as first apply phi and then apply theta. So it has this universal property. So you could have defined sim AV to be a vector space which satisfy this universal property, and then show the existence by taking this quotient by of the tensor algebra tensor power by the drill in that subspace. Yeah. So I mean, the proof is sort of similar to what we have been doing. So I didn't write, but maybe I can tell you what how to construct theta tilde, and so yeah, I mean, when there is only one way to do it, then it's sort of easier. Yeah. So what should be theta tilde of sim AV looks like this guy. Yeah. So a typical element, it's a quotient of this tensor power. Yeah. So as some V1 to VA, where so it's sums of these things. So that's not, yeah, so sums of these kind of thing. But once we know where theta tilde takes these guys, then we will know the rest. Yeah. So where should theta tilde send V1 to VA? The product.
It should be like theta V1 to V.
It's just theta V1 to V. Yeah. Or so more rigorous way of doing it is see, theta defines a map from V cross A copies of V cross V to U, which is multilinear. Yeah. Then of course any multilinear map factors to the tensor product. Yeah. So theta will factor through TAV to U by definition, by universal property of tensor algebra, tensor products. And then since theta is symmetric, it will be 0 on this subspace. Yeah. So it will be 0 on this subspace. So that tells you that the kernel will kernel of that. So another way of thinking of it is theta induces maybe theta 1 tilde from V cross V A times to TAV. Yeah. And theta 1 tilde is going to be which sends V1 to VA to the tensor powers. Yeah. Because theta is multilinear, and since theta is symmetric, Symmetric, yeah. So symmetric multilinear form precisely means this. Yeah. Symmetric multilinear map precisely means this, that if you this condition should hold. Yeah. So since theta is symmetric, that tells you that this the subspace this it sorry, not what I meant was sorry. So this is nonsense. So what I meant was there exists a unique map from so since this is multilinear, there exists a unique map from TAV to U, which sends V1 tensor VA to theta of V1. I mean, there is a canonical map from V cross V cross V to TAV, which sends the A tuple V1 to VA to this tensor power. Yeah, that is the multilinear map you start with when you have a so that's part of the definition of TAV. Yeah. And TAV has the universal property that given any multilinear map to any other vector space, it factors through TAV. Yeah, so theta V1 to theta to VA. Yeah. So giving a map from A copies of V to U is same as a multilinear map from A copies of V to U is same as giving a linear map from TAV to U. Okay, so theta 1 tilde is a k-linear map, and note that since theta is symmetric, that tells you that V1 to VA and V sigma 1 to V sigma A, they will map to the same guy. Yeah, symmetric means precisely that. So so that tells you that this subspace will go to 0. So that subspace is in the kernel, so that will induce a unique map theta tilde from this mod the kernel or this mod that subspace by first isomorphism theorem. Now use first isomorphism. First isomorphism. And that definition will give you that this is your theta tilde. Yeah. So V1 dot VA will then go to theta of V1 to VA. Okay. And by construction, this diagram will come. So that's the proof of the fact that CMAV is the universal object. So it satisfies the universal property. Okay, so I'm not doing it very rigorously, or not writing all the details, because it's sort of similar to what we did last time. Yeah. So so this is how symmetric powers are defined. Now, what is a basis of? So remember, TAV, the basis were all tensors. Yeah. So if you had a basis V1 to Vn of V, then you take VI1 to VIA, tensors of I1 to VIA, where VIs are where I1 to IA are between 1 and n. Yeah. But for symmetric, of course, V1 tensor V2 should be same as V2 tensor V. They map to the same guy. Yeah. So of course, you both can't be part of the vector, part of the basis. They actually map to the same guy. So in fact, if E1 to En is a basis of V, then for sim AV, the base. So if you consider so these are the elements. Yeah. So I said our notation will be this way. Yeah. V1 dot VA is basically the image of this guy. Yeah. So EI1 dot EIA This is basically image of you take the tensor powers and take its image. Yeah. So this with I1 to IA between 1 and n, but now you put an ordering, yeah? Because you don't want both I1 and I2 there. Yeah. So this is going to be a basis of sim AV. Okay. So maybe this I'll assign it as a homework problem. Yeah. So it's not difficult. Yeah. So maybe you can so this will certainly generate sim AV. You have to show that it's linearly independent. Okay. Or yeah, you can yeah. So maybe you just try to show it's linearly independent. So. Okay, so there are no other relations. Using the fact that in tensors there are no other relations. Yeah. So tensor product TAV is generated by it has a basis EI1 tensor EIA and so on with where these EIs so I1 to I2 they need not be ordered. So you use that and somehow show that. Okay.
So
Yeah.
just a doubt. So instead of if we is this same as if we add some abelian relations to your TA, would we get the same thing?
So what abelian relations?
Say for example, if we identify AB with BA.
So that is what we
T2B, for example.
So
this is just a abelianization of that TAV. Not exactly.
But what does abelianization? I mean, it's just a vector space TAV. Yeah.
Yeah, I see.
So for so if you look at tensor algebra, then yeah, so you quotient it out by V tensor W minus W tensor V, then the ideal generated by then it is true. Yeah. So I'll come to it. Yeah, but at the moment there is no algebra, there is no multiplication structure. Yeah, it's just
okay.
So you can't do it.
Okay, thank you.
Yeah, welcome. Yeah, so this is a basis, and maybe you can using this you can also calculate the dimension. Yeah, so what is the dimension of sim AV if you are given that this is a basis? So if V has dimension n, then
it would be like n plus a minus 1 choose n minus 1.
Say that again.
Sir, n plus a minus 1 choose a minus n minus 1.
Plus a minus 1 choose
n minus
a minus 1. Yeah?
So n minus 1 or a, either way, n minus
1. So you have to, so this is some sticks and stuff, yeah? You have to, there are yeah, so there are n things which you have to divide into a guys. Yeah, so maybe.
I think it would be like n minus 1. Yes. Yes.
Yeah. Is this okay?
Yes, sir.
Yeah. So this is what you get. Yeah. Sim AV is going to be so it's basically how we are trying to calculate the number of basis vector using just combinatorics. Yeah. So you have to divide 1 to n in a so I1 will divide it into one part, I2 to 2 part. So a plus 1 pieces, yeah. So So you have to choose, yeah, so you can put here A, yeah, so maybe that that interpretation gets, yeah, so you have to, so it's like, you have n objects and you want to divide it into A+1 guys. So you add a sticks, and then you choose those sticks, and so this combinatorial interpretation, I hope, yeah. So whatever, if you are convinced that this is this, then it's okay. So this is how I keep it in my head. So this is of course same as n plus. So there may be another combinatorial way, which he was saying. So of thinking about it. So both are same, yeah. So this is the dimension of the. So this, of course, is less than. In general, it is for tensor algebra. This is n power a. So this is far less. Yeah. And if V and W are two vector spaces, and you do so the sim A V plus W, it splits into symmetric thing in this way. So this is isomorphic to sim IV tensor sim A minus IW, where I runs from, and then you take the direct sum over I equals 0 to. Yeah. So maybe one can write this some more explicitly. So if I is 0, then sim 0 V, remember, is just K. So it is K tensor sim AW direct sum V. So which is basically, so maybe which is same as sim AW. Yeah, tensor by K doesn't do anything. So meaning tensor with K is isomorphic to the guy you started. And V tensor sim A minus 1 W plus sim 2V tensor sim A minus 2 W, and so on. And so on. Yeah.
Then, can you please explain this once again?
Say that again.
Can you please explain this property once again?
Yeah, I'm trying to tell you that if you have two vector spaces V and W, then sim A of V plus W is isomorphic to this guy. And I'm just trying to expand this. So I'll tell you why these two are isomorphic. I'm just trying to say how the right hand side looks like more explicitly. Yeah.
Yeah.
I'll tell you. Is that your question about this problem?
Yeah, that was my question. Yeah.
Okay. Yeah. So I'll explain how you get at least I'll give some idea. Yeah. So first of all, there is a linear map. Yeah. So maybe you take one particular factor, sim IV, to sim A minus IW. Then you have a k-linear map from. So this is isomorphism of vector spaces. Yeah. So and it's a natural map. Yeah. So remember, so of course, if you take an element of sim IV, V1 to V dot I, and sim A minus IW, which is W1 to WA minus I. So hold on a second. Yeah. Okay, so we have this map from sim IV to sim A cross sim A minus IW to sim A V plus W, which is this pair V1 to V dot I. So I mean, okay, so basically one should take sums of this. A typical element here doesn't look like just product of this, but sums of this, and here also sums of this. But you expand it linearly, yeah. But so on these kind of guy, you just send it to this comma this to this product, okay. So by definition, this is going to be a bilinear map from forget about the tensor for the moment. It will be a bilinear map from sim IV plus sim A minus IW to sim A of V direct sum W. Yeah. And since this is a bilinear map, it factors through the tensor product. So you'll get a map from this tensor disk to this guy. So that is our theta I. Yeah. So theta I corresponds to the bilinear map. Sim IV cross sim A minus IW to sim. So I'm just trying to tell you more precisely how this maps are given. Yeah. So corresponds to this bilinear map. So every such bilinear map corresponds to a map, a k-linear map from tensor product to this guy. So this is your theta I. And then to give a map, so I'm trying to give you a map first in the other direction from right on the right hand side to this. So theta is just the direct sum of these maps. Yeah. So theta is just direct sum of these thetas. So you'll get so on each piece you have a map to sim AV. You can just add them to get a map from the direct sum of these guys to this. Yeah. Does this make sense? The map theta I and then this theta.
So I don't see why it's an isomorphism theta.
Yeah, but the map makes sense. Yeah.
Yeah.
Yeah. So we'll come to why it is an isomorphism. Yeah. So so now we want to give you so I'll roughly tell you why this is an isomorphism. Yeah. So it's one can check whether it's injective. So you basically you can check each theta is injective, and then maybe and it's surjective. But maybe I'll convince you that there is an inverse map as well. Yeah. Because it's sort of canonical, maybe it's best way to do. Yeah. So let's V1 to Vn be a basis of V and W1 to Wm be a basis of W. Then if I take any alpha in sim A V plus W, then sim A is basically a quotient of the tensor algebra, and for tensor algebra at least we have seen that this forms a basis. Yeah. And this, in fact, and at least when we take J1 less equals J, so even if we make sure that these inequalities are whole, then also this generate, because any other permutation will map to the same one of these guys. Yeah. So any typical alpha you can write it like this. Yeah. So if you assume that this basis statement holds, then this is there, but generation part is not a problem. Yeah. So alpha typically looks like this, and then but if you know that this is a basis, then it's you just say where this basis vector go. Yeah. So there will be certain number of copies. So it will be sums of these kind of tensors. And in each pure tensors, there will be some copies of VIs and some copies of WJs. Yeah, so some of them will be in V, and the remaining will be in W. Okay. Because this does form a basis of these tensors does form a basis of V plus W. Yeah. So V1 to Vn, comma W1 to Wm is a basis of V plus W. So you can write it this way. So you collect all the terms which lie in V and order them in this way, and you get something like this. So of course, this particular element of sim AV plus W, you map it to an element of the domain of theta I. Yeah. So C of alpha, you define it to be on this factor, you define it to be Vj1 to Vji. Okay, tensor Wji plus 1 to Wja. Okay, the images of these things in so this the first factor lies in sim IV, and the second factor will lie in sim A minus IW. Yeah, and then you just sum it. Yeah, so on the individual component, you just send it to whatever that is. Okay. So C will also, I mean, we have defined it using, so now you extend it linear. So we have defined it, the way we have defined it, it is linear. Yeah, so check C is K linear. Okay. And then the point is theta and C are inverses to each other. So one has, so I guess it's clear, right? I hope this is clear that theta and C are inverses to each other. Yeah. Is that okay?
Yes. This part about its well-definedness, we need to check.
Yeah. So well-definedness. Yeah. So. So that two way, either you do it using the basis argument, well-definedness, or otherwise you'll have to sort of work with this tensor product and so on. Yeah.
Okay, sir.
Okay. So so you show that this does form a basis, and then of course well-definedness is not an issue. Yeah. Or other ways to show that. Show using using tensor products. So universal properties of tensor product. So the point is, this is a quotient of the tensor algebra. Yeah. So you sim AV plus W. Yeah. So you look at TAV plus W, and there again same property holds. Yeah. So I think it's best, yeah. So you can do the universal property, but I think it will be simpler to do it using basis, yeah? Since you haven't seen tensor products that much, yeah? So maybe it's a good idea to do it using basis. Okay. Yeah. Okay. So yeah. So that tells you that they are inverses to each other. Yeah, so maybe let me see if I can give you a quick way of saying why it is well defined using the tensor thing. So yeah, so TAV plus W is there. Yeah. So I want to give a map from yeah. So I'll have to give you a map from yeah. So this is okay. So
Sir?
yeah.
Yeah, so I was thinking this like in sim A we direct some W,
these elements Vj1 tensor Vji, then tensor Wji plus 1, tensor Wja. So here these elements of V and W can be in any order, right? Means it is not necessary that V's are grouped together and W's are grouped together. But for all such elements, we can pick such a representative, right?
Yeah,
that
yeah.
V's are together and W's are together.
Yeah, yeah.
So, I mean, then, like, isn't it clear that
Yeah,
it is well defined after?
yeah. So by yeah, so I was trying to yeah. So that is the idea. So, but that but still you have to say that this forms a basis. Yeah. So there may be relations among this. So if you assume that this is a basis, I mean.
Yeah, like I was assuming that. So.
Yeah, if you assume this is a basis, then it is clear. Yeah, I'm trying to tell you, give you an argument more without using that is a basis. Yeah. Okay. So you by just looking at the universal properties. So if you do use that basis thing, then it is okay. I was trying to give you more canonical. So V plus W. There's A copies of V plus W to so maybe write it as product. I equals 1 to A to TA V plus W. Yeah, this is your map, and so I want to. So if I want to give a map from sim A V plus W to the right hand side, I'll have to give you a symmetric multilinear map from this to, so I'll have to first give you a multilinear map from this to this right hand side. So it is okay. Yeah. So it is. So what does this look like? So it's A tuples of vectors. Yeah. So. So it's A tuples of vectors, and those vectors you can uniquely write it as AI VI plus BJ WJ and so on. Yeah. So yeah. So you'll have to send it. So it will become a bit complicated to write it down. That's why maybe yeah. So I can only tell if I tell you where the basis vectors go, that is enough. Yeah. So and then you extend it linearly. So V1 VI1. So yeah, so there are A copies of these. Yeah, so that is yeah. So I don't know. So the vector yeah. So B yeah. Yeah, so roughly speaking, so some some I of them. So in the first I of them, maybe only V comes, and the remaining A minus I of them, the W comes. So any typical element here will look like sums of these kind of guys where I varies. Okay. A typical element of the A copies of V plus W, yeah, and then you send it to the appropriate summand here, okay, and then you just check that this map when you extend it linearly is both symmetric and is multilinear and symmetric. Okay, so it will factor through sim A V plus W. Okay, so so it if I try to write it here, it will become very complicated. So you can try it yourself. Yeah. So in a systematic way, if you write, then so give a map to the sum of sim I V tensor sim A minus I W, yeah, I equals 0 to A. So depending upon how so the basis basis of this has so in the first component you take a basis of a V or a basis vector of V or a basis vector of W, and second component you take a basis vector of V or basis vector of W, and so on in the eighth component. So whether the first component you took a basis vector of V or so in the first, how many component you took basis vector of V or basis vector of W, depending upon that you will choose which I, what should be your I. Yeah. So if there are I components in which you took basis vector of V, then it should map to sim IV tensor sim A minus IW, and so that will give you a basis of the whole basis of V plus W, A copies of V plus W, and then you extend it linearly, and then you show that this is multilinear. So by since you are extending it linearly, it will be multilinear, and then since it's going into the symmetric, it will be symmetric multilinear map, and then use the universal property to say that it actually factors through sim A V plus W. Okay, so directly you can get a map from this to this. Okay, so that's another way of doing it. Okay, and then checking that theta and C are inverses is pretty straightforward. You just check it on basis, yeah, or a generating set that they are when you compose them in whatever order, you get identity. Okay, and then okay, so maybe I'll just state the symmetric algebra is just direct sum of these guys. So sim V by definition is but I should also define the map, yeah. So so of course there is a natural map from sim A V cross sim B V to sim A plus B V, which is just you know, which will send V1 to VA, comma V1 prime to V prime. So this is how elements here look. Sums of this are typical elements. Yeah. So like we defined in the tensor is the same kind of. Yeah, Bello, thank you. This goes to V1 dot VA, V1 prime. Okay. So this is the product map. Yeah. So sim. So as I said, we'll not talk much about this by is the symmetric algebra. Okay. With product defined above. One. Hold. Okay. So this is the symmetric algebra. Yeah. So as you can see, symmetric powers, you can write it as quotients of tensor powers, and we will show that you can think of it as something contained in the tensor powers as well. But let me just define similarly the exterior powers. But so similarly, one can define exterior powers, yeah. And more or less, yeah. So same along the same line. So that that we be as above. Then this, yeah, so one can define it, as I said, using quotients of tensor power or using the universal property. So maybe first using the quotient of tensor powers. So TAV, so this time you go more, so it should be universal towards not symmetric multilinear map, but anti-symmetric multilinear map, yeah. So that means phi of V1 to Vn is not same as phi of, yeah, maybe I should write down what, and symmetric multilinear map was okay, but maybe, yeah, so let me just first write what is symmetric antilinear map. So let multilinear map, linear map phi from V cross V to another vector space U. So this is A copies, let's say, is called antilinear. If phi of V1 to VA is not same as phi of V sigma 1 to V sigma A, but almost, yeah. So it's only difference is by sine sigma for all sigma in SA. Yeah, and this is the symmetric group. So this is what, so I should have defined symmetric multilinear map as well, but I suppose not antilinear, but antisymmetric. So antisymmetric is this. Symmetric means you drop this sign thing, yeah, which we use there. So exterior power is either you can think of it as the universal object for these kind of maps, or you can quotient it out by this some subspace where you equate these kind of guys. But one good thing about so the subspace generated by, so the subspace okay, V1 to VA minus sine sigma V sigma 1 to V sigma A, sigma in SA, Vi is in V. This subspace is actually same as, you just take two of them identical, then also you get the same subspace. Yeah? So this is same as V1 to VA, whereas VI equals VJ for some I not equal to J between 1 and A. Okay, so the subspace that is because, so first thing to note is that if I this is from this observation that if we have V1 so if phi is anti-symmetric, yeah, so how do I say this? Yeah. So this is some observation. So the point is, so if you consider V tensor V, yeah, I want to say that you can write it like this. You can write it as in this space and conversely, yeah. So V tensor V is yeah, so I mean, this of course is in the subspace generated by this because V tensor V. So if two of them are two of them are same, then you consider the permutation. So consider this IJ in SA, then V1. So yeah, so what am I trying to say? So what I'm trying to say is you go mod this subspace or this subspace, you'll get the same answer. Okay. So yeah. Yeah, so maybe
But so the sign of this is this is sorry. So we get that this belongs to the first one, right?
yeah, so
Because this is an odd permutation.
yeah, this is an odd part.
So
you take
we get
IJ
that.
and then this is and this subspace. So why is this in the previous guy? So I thought. So how can I write it as if two of the so if two of them are same, then I can
we get
write
that?
it.
Yeah. So V1 we just exchange VI and VJ,
Yeah,
and
so
then we bring it to the other side.
yeah, V1. So maybe there are only two terms. Yeah, so VI, VJ minus sign of sign of IJ is -1. Yeah, so we just interchange I and jth pieces of this tensor. Yeah, so you consider yeah, still Now, how do I write it as this minus sine of ij? Okay, so let's just try to, okay. So I have, yeah, it's better done privately, but okay. V1 tensor Vi minus 1 tensor Vi tensor V. So here again you get the same Vj minus 1, and here you again get Vi Vj plus 1.
So we want to set Bi the exterior product with Vj to be equal to minus Vj exterior product Vi, right?
Yeah. So I wanted to say that the quotient of these two are the same. Yeah. So but maybe it's better to. So
Like
yeah.
what?
So if you apply sigma to the yeah. So yeah. So we so some basic identity is needed. Yeah. So something like this. So this is V tensor W plus okay.
Sir,
Yes, tell me.
so
Yeah.
we want to say that this minus sign of this is equal to 0 if and only if the thing in the bottom is.
Yeah, exactly.
So-
So this is 0 if and only if
two terms when they're equal.
yeah. So yeah, so this is true, but somehow I'm not able to tell you why. Yeah.
So if we have V1 to Vi and then Vjth is also Vi, then if you apply that sigma ij sigma equal to
Ij, yeah.
then you get this upar wala thing
Then
is
I get
times
that this, yeah. So yeah. So on yeah. So maybe that maybe trying to show the two subspaces are same is a bit more complicated. But the note that let's call it H. H is going to be kernel of H is so if so what so if um, uh, uh, so and H prime is this. Yeah, so I want to say that TA mod H is same as TA mod H prime. So it's not some isomorphism. They are the H and H prime are the same subspace. Yeah. So you take some vectors, go mod H. That yeah. So what you can try to do is you take anything in H prime and go mod H. Look at his image in this guy, then you get 0. Yeah, that is clear. And similarly, you take so that tells you that H prime actually lies in the is contained in H, and similarly you do the other thing. Yeah, so H prime mod H intersection H prime possibly is 0. Check. So this is what is easier to verify, and H mod H intersection H prime is also 0. So that tells you that both of them must be must be the same vector, same subspace. Okay, so their images in the corresponding quotients are same. Yeah. So TAV you can quotient out either by this or that to get the exterior powers. Yeah. So define. Yeah. So I've wasted all my time on this stupid thing, but it's TAV mod H prime. Okay. Okay. So this is the exterior power. Maybe since we are over time, I'll just complete the parallel thing tomorrow. Yeah. So I'll tell you more about. So I'll do the parallel analogy tomorrow about the exterior power, and then we will show that both the exterior power and symmetric power you can write it as subspaces of SymAV. And
so can we do this? So say x1. So x1 exterior product with xi until xi plus aj, xi plus xj, then product with. So basically, just add the two. We have xi and xj, and then you have them replaced together like xj and xi, right? So we want to prove that xi product exterior product with xj is equal to minus xj exterior product with xi. So we start with this. That's what our first subspace is. So we have 0 equal to xi plus xj exterior product xi plus xj, right?
You are trying to give
So
me an
basically we
argument for why h and h prime are same.
Sorry. Yeah. So we start with one element of h. Say it was everything we are doing is for this two-dimensional. Then we have xi xj, and we want to show it. Then xi xj minus. Then sigma is equal to I and j. Then that becomes plus because it's an odd permutation.
Yeah, so I think there's some
yeah, so that sums to 0 equal to. So we have xi plus xj.
So maybe there's some basic identity which maybe I should have. So
basically after adding we get xi plus xj product xi plus xj, and then we break along xi product xi and xj product xj.
So maybe you expand this, yeah, v plus w tensor with v plus w. What do you get? You get v tensor w, yeah, plus v
tensor v
w tensor v. I think this is what it is, yeah. So v tensor v and plus w tensor w.
Yeah, so and then and this is equal to 0.
So you move this the other side, so you get v tensor v plus w tensor w minus v plus w tensor v plus w. So this is the basic step which I was forgetting, yeah, is same as v tensor w plus w tensor v, yeah, which is same as negative of, so I can write it as, no, I can't write it as that, but yeah, is plus sine of, so whatever is the permutation, yeah, so I have to, I didn't use ij, but what is w tensor v, yeah. So if so switching the order, so if the left hand side is 0, then the right hand side is 0, and right hand side is precisely the elements of h, yeah, and left hand side are precisely the elements of h prime. And conversely, if so that's how you show that the two subspaces are same. Okay, so you just use this basic identity. So from here, you can show that h and h prime are same subspace. This is the argument you were trying to give, yeah?
Yeah.
Hopefully, some variant of this. Yeah. So some variant of this argument is what goes into saying that this happens. Okay. So let me stop.